All right, good afternoon, everyone. Please take a seat so we can get started with today's lecture. All right, so welcome everybody to today's class in Mathematics 1. Before we start, a quick organizational announcement. We will start the evaluation of this course here, I think sometime by the end of November. To be able to participate in that evaluation, you need to please register for this course on TUM online. Please do register for the lecture class. All the rest is not important, but the lecture class. That's simply because I export the emails from that TUM online system, and then you'll all get a unique number that enables you to participate in the evaluation. And of course, I would appreciate a high participation to get good feedback. So if you haven't done so, please remember to register for this course on campus.tum.de. Otherwise, you won't be able to participate in the evaluation. All right. Let's take a look at this week's topics. I trust you have all watched the videos for week 4. And in week 4, we mainly talk about 2 different topics. The first one is going to be a little appendix to last week's topics. We're talking about affine spaces a little bit. You will have noticed that I slipped the name of affine spaces already sometime last week. And now we'll finally formally define what that is and where we can use them. Second major topic of this week is going to be matrices. That should hopefully be something that is pretty straightforward. So formally, matrix is not that exciting, pretty similar to the vectors that you know already. And you will find that we have already worked with matrices. We just call them tableaus up to this point. The one thing that is probably new to most of you is we are going to introduce a multiplication operation for matrices. And this multiplication is somewhat of a strange beast because it's not quite the same thing as multiplying 2 numbers. So it has some properties that you might not be used to. And we'll talk about this multiplication a little more this week and also next week. All right, so that's an overview of the main topics. Let's start with a quick look at affine spaces. So here's the formal definition. We have a vector space, we call that V. Oops. And we call a subset of that vector space an affine space if it resembles a linear subspace plus some translation. Right? So if there is a linear subspace such that our subset S can be written in this form, S plus U, S is a constant vector contained in capital S, and U is some linear subspace. So we've seen some prominent examples already. Picture, for example, in R2, a possible type of subspaces in R2 are lines through the origin. So this is a typical linear subspace. And if we translate that by any vector that we want, we get an affine subspace. And translation basically means we get a line that is parallel to this one. For example, in this case, this here might be our vector S. This is our space U. So the blue thing, that is S plus U. Right? For every point on U, we just add that S. So we translate it, every point we translate in the same way, and we just get a translated line. And of course, any other point, any other vector on that line would have worked in the same way. For example, you could use this one here. Right? That's also a possible S. small s, and it gives you the same translated line. So the choice of this small s is usually not unique. Far from it. Yeah, so that's the typical example in R2. Of course, you also have your one-dimensional vector spaces, like this one here, whoops, the origin. Sorry, zero-dimensional vector spaces. So that's a zero-dimensional subspace. And if I go ahead and translate that, let's take this here as a translation vector. What I get is, again, a point. So the points in the plane are also affine subspaces in R2. Right? Well, those are the zero-dimensional affine subspaces. And I can simply define the dimension of an affine space to be the dimension of the associated linear subspace. Okay, so if I want to know the dimension of some affine space, I basically have to translate it back such that it contains the origin, and then I look at the result. That's a vector space, and that has a dimension. And I just use that dimension. Okay, so that's affine spaces. And we've already used a couple of common names for affine spaces. A subspace of dimension 0 is called a point. We've just seen that. If I have dimension 1, that's called a line. Dimension 2 is often called a plane. And in general, the dimension of the surrounding vector space -1, that's usually referred to as a hyperplane. So in R3, in three-dimensional space, a plane and a hyperplane are the same thing. In R4, they would be different. Right? A plane is two-dimensional. In R4, a hyperplane in R4 would be three-dimensional. All right, but we rarely use hyperplanes. We often use points and lines. Okay, so in short, an affine subspace is equal to a linear subspace plus some constant translation. All right, we've seen a couple examples already, so I can skip over that one. Then, similar to the concept of a span, as you remember, a span is the smallest linear subspace that contains a given number of points. Right? So you start with a finite point set. You want the smallest linear subspace that contains all these points. That is their span. And a similar thing can be done for affine subspaces. You start with any number of points. You want the smallest affine subspace that contains all of these, and that is called the affine hull. So again, let's consider a quick example. In R2, if we just start with a point, and we want the smallest affine subspace that contains this point, the result is, of course, just that point, because that is already an affine subspace, right? We just talked about that. If I want an affine subspace that contains 2 points, let's say I want this point and this one. And I want the smallest affine subspace that contains both of them. What do I have to do? Well, I need to take the line that is defined by those 2 points here. So this here, right? That is the affine hull of those 2 points. Similarly, if I take 3 points, let's also do that. So let's say I have these 3 points here. What's the smallest affine subspace that contains all of these? Obviously, they are not all on one line, right? So one line won't do. What's the next possible step? The plane, exactly. So what I need here is the whole plane, all of R2, right? So that's the concept of affine hulls. It's basically the same thing as a span, but it generates an affine space and not a vector space. All right, I won't go through that computations here. How can I generate a span computationally? Well, what I have to do here is similar to the linear combinations that we've seen with vector spaces. You remember a linear combination of a vector space or of a set of vectors is something like that. And a span is the set of all possible linear combinations. For an affine hull, you can do a similar thing. It's called an affine combination. And the only difference is you need to restrict your lambdas. Right? So with spans, those are arbitrary lambdas from the reals. If you want an affine combination, you restrict them to be equal to 1 in their sum. Let's again take a quick look at a sketch that hopefully illustrates that. So let's say we want to consider the affine hull of this point here, and maybe that point. Right? We already said the affine hull of those 2 points. That is a line that passes through them, so that is their affine hull. And how do we generate a point on that line? For example, let's start with taking just this vector here. Then, of course, we get 1 point on the line. Right? So that's, let's say this is vector v1. Oops, sorry, v. This is v1. This is v2. So this point here, that is 1 times v1. This point here, of course, is 1 times v2, right? That's simple. Now let's say I decrease my v1, so I scale down v1 a little and increase v2 like that, and I get this point here. Right, so here I have some amount of v1 plus some amount of v2. That approximately, that should be something like 1/2 v1 plus 1/2 v2. Not quite, almost. And you can see if I decrease v1, if I decrease that a little and increase v2 on the other hand, then I get points like this until I'm at this point here, right? So between this point and that point, I decrease the amount of v1, I increase the amount of v2, I'm on that connection here somewhere. And now if I go further, if I decrease v1 further, sorry, what happens is I go into the negatives. And as the sum of those 2 lambdas needs to be 1, that means the lambda for v2, lambda 2 has to increase beyond 1 to make up for that. Right, so what we get here is this here. Right, so that would be something like roughly minus v1 plus 2v2. Right, and again I'm on line. And of course I can do the same thing if I go in this direction, right? I increase v1 and I have to go into the negative with v2 at that point. I get something like up here, and then I need to go in that negative v2 direction. And as long as they balance out, as long as the coefficients are equal to 1 in their sum, I'm always staying on that line. That's the basic idea of an affine combination. All right? That will mostly not be important. Just so you know, there is a way to express elements of an affine hull in almost the same way as with vector spaces, with spans, linear combinations, but with a little added restriction on top. Okay. And finally, the one theorem that is the reason for talking about affine spaces at all. You remember that last week we said the solution set of a homogeneous system of linear equations is a linear subspace of R to the n. And we also said for an inhomogeneous system, the solution set can be obtained as the solution set of the homogeneous space plus one particular solution of the inhomogeneous system. And that, of course, is just the same thing as saying, well, the solution set of the inhomogeneous system is an affine subspace. And that vector space that belongs to it is just the solution set of the homogeneous system. Right? And that is the summary of that theorem here. So if I have a system of linear equations here in n variables, then the solution space is an affine subspace of R to the n. And its dimension is the same as the dimension of the solution space of the homogeneous system. So that is n minus the rank of this A part of my tableau. All right, affine spaces. Let's take a moment to answer a couple of questions about affine spaces. I have two quick quiz questions that I'd like you to answer. Here's the tweetback link for this week, so please use that. And let's see what answers you get. Again, it's two true or false questions. The first one is true or false, each vector space is also an affine space. And the second one is true or false, if S is an affine space, and I take any element T in that space, then minus T plus S is a vector space. Is that true or not? And as usual, if you have any questions, you're welcome to also ask them on feedback or live. I'll give you a few minutes afterwards. All right, I'll give you 10 more seconds to answer the quiz questions. And then let's take a quick look. So true or false, each vector space is also an affine space. Most of you said true. And of course, that is correct. The explanation is simply that, well, an affine space is something that looks like S plus U for some point S in the space and some linear subspace U. And of course, there's nothing that prevents me to use the zero vector here. And 0 plus U is just U. Right? So any linear subspace conforms to the definition of an affine subspace. That's totally fine. Yeah, linear subspace is a special case of an affine subspace. So let's see the other question here. If I have an affine space, so I have a space S, that's an affine space, and I take some element, let's call that T in S, and then I'll look at minus T plus S. My question is that a vector space? And most of you said yes, and of course that's again correct. Right? So if I take any element in that space and translate the whole space back by that element, then I basically redo or undo the translation that was in place in the first time. So I move the space back to pass through the origin. It now will contain the origin because that element T, right, this here, this T is contained in S. How do I say that? So T is in S. So that means minus T plus T is contained in that set minus T plus S. And minus T plus T is just the origin. Right? So now my space does contain the origin, and then it's just the linear subspace that's left. All right, that is going a little better than last week. Okay, a couple questions. Let's see what questions we have here. First thing I like to answer is, someone asked if we have a line that goes through the origin, any point can be expressed by a linear combination of the vectors 1, 0, and 0, 1. Let's make a quick sketch. So we are in the plane, R2, and we have a line that goes through the origin, like that. So that's our line. And then the person says any point on that line, let's take this point here, for example, that can be expressed as linear combination of two vectors, 0, 1, 1, 0, and 0, 1, right? So this is 1, 0, that is 0, 1. And of course, well, just have to find the right lambdas here, so I need to scale this up and scale this one up as well till I get to that point. So that can be expressed as a linear combination. Right? That's of course true for every point on the line. Another question is, doesn't that mean that those two vectors represent a possible basis of that line, given they are linearly independent? Well, is that true? Are those two a basis? I mean, the line obviously is a linear subspace, so are those two a basis of that line? Any thoughts on that? Yes. Yep, so you're saying the two vectors are a basis for the whole plane, right? That's true. And the line is contained in the plane, so yeah, the line can obviously be created by those two, and they are linearly independent. Everyone agree? I hope not. What is wrong with that argument? There's a subtle point missing here. I mean, you do remember that we always said a line is a one-dimensional vector space, right? So how can there be a basis that has two elements? Something must be wrong. Yep. Sorry? They're not linearly independent, they are. I won't do the computations, but you can verify that easily. So both is right, yeah? You can generate every point on the line with these two vectors. Obviously, you can generate the whole plane, and they are linearly independent. Let me show you a basis of that line that only contains one vector. For example, I could use this here. Just this yellow vector. That also generates every point on the line, and it's just one non-zero vector, so it's linearly independent. So that is also a basis, right? How can there be two bases that have different cardinality? Yeah. So you're saying those two, the blue ones are a basis for the whole plane and the yellow one is just for the line. Why are the blue ones not a basis for the line? Exactly, they're not on the line. That's the point, right? Basis vectors have to be contained in the space that we're talking about, and those are not on the line. So they're not contained in the space that we're considering. So it doesn't matter whether they span it or not, they're not even in that space, so they can't be a basis, right? So that's a takeaway message, I guess. A basis has to be contained in the vector space that we are considering. And in this case, the line is the vector space that we consider. And neither this nor this vector is contained in that line. The yellow one, that is contained in the line, yeah, so that's fine. And if of course, I could try to scale them such that they are on the line, and if I do so, the result is I have to scale them back until they become 0, and then they're neither generating the line nor are they linearly independent anymore. So that doesn't work. Okay, so I hope that that answers this question. Nice question, by the way. Here's another one. Does the affine combination allow us to reach every single point in an affine space? Well, it has been asked before the start of this course. I hope that question has been answered already. Just to be sure, the answer is yes. An affine combination allows us to reach every single point in affine space. All right. Does every translation vector have to go through the origin? Well, in a way, yes. So if I'm translating something, I usually start my translation at some point. And if I don't specify a different point, then that is the origin. Let me just make a quick sketch, right? So, I mean, if I have a line like this here, of course, that's a translated linear subspace, and one possible translation vector is, let's take this one here. Of course, I could combine that. I could say, I'll start with this here, and then I'll translate that much. And in this case, the second translation starts here and not at the origin. Yeah? And in some cases, it will be useful to consider a translation as a combination of two different translations. Right? Shift left first and then up or something like that. And I'm interested in the final result. But usually we'll consider the sum. I mean, we are only interested in the outcome, so the final effect. And it doesn't really matter whether I shift right and then up or whether I just shift that way. Same thing. Okay, so usually we just consider the net effect, and that starts at the origin. All right. Oh, there's a nice question about the evaluation. Will it be graded? So just to make sure you understand that correctly, evaluation means that you evaluate me and not the other way around. This other thing is called exam. It's going to be at the end of the semester. That will be graded. I'm not sure whether there's grades in the evaluation, but there's something like point scale. So basically, yes, you can say it will be graded, but that's a grade for me, not for you. Are we also going to talk about convex combinations? Nice point. Where did you discuss convex combinations? Does anyone know the term convex combination? No? Okay, so I'm not going to go a lot deeper in that. I'll just let you know what that is. Basically, similar to the affine combination. So again, you have a couple of vectors, k vectors, and a couple of scalars, k scalars, and you do something like a linear combination of those. And now there's, for a convex combination, there is two restrictions. The first one is, again, the sum of the lambdas equals 1. So that's an affine combination. And the second is all the lambda I are non-negative. And what that means geometrically is basically if you have those 2 points again, this and that one. And so here's the vectors that can be used. Taking this vector once will result in this point, and now I reduce this a little, and I add a bit of that vector instead. So I'm getting points somewhere here on the connection until I hit this point. At this point, this other vector has a factor of 1, and the other is reduced to 0. And if I wanted to go further, if I wanted to go there, down here, right? I'd need to extend this vector and go in the negative direction of the other one, like this, for example. Yeah. I can do this in affine combinations. I can't do this in convex combinations. That's the difference. And geometrically speaking, what I get with a convex combination is the line connecting those 2 points, but then cut off at the points. I'm not going further than those points, right? So this part here and also this part up here, that is not part of the convex combination. But just in case you encounter that somewhere, and just because it has been asked, we will not need that term anywhere. All right, an affine space can be a vector space, but not every vector space can be an affine space. So one by one, an affine space can be a vector space. That is, of course, true because every vector space is an affine space. So here's a vector space, right? And I can, of course, write this as 0 plus u. We've just discussed this. So that is also an affine space. Every vector space is also an affine space, but not the other way around. Right? So every vector space is an affine space, but not vice versa. Right? There are affine spaces that are not vector spaces. For example, this one. Right? That does not contain the origin, can't be a vector space, but obviously it's a translation of this orange space, so it's an affine space. Right? So there's lots of affine spaces that aren't vector spaces, but some of them are. The ones that contain the origin, to be precise. All right, I hope that answers this question. So, any more questions on affine spaces or vector spaces? Otherwise, we'll have a look at some examples before we go on. It does not seem to be the case right now. All right, then the next thing I like to do is have a quick look at part of the homework, at 4.2. So I'd like to discuss this exercise 4.2 quickly. Just see how you did there. So the question here is determine the dimension and the basis for the linear subspace given in this way, the span of those 3 vectors in R3. And my first question is, what is the dimension? So, where's my mouse pointer? Here. Again, let's go on tweetback and see if you can answer that. And of course, I'd also like to know how difficult you found that for 2. You all did this already, so I'll give you 30 more seconds. That is an interesting result. Just switch over here. All right, so that's how hard you found it. Some found it hard. I think most of you are leaning at least left of the middle towards the easy part, but obviously not everybody. And here's the result. So you seem to be undecided on that one. Probably it's either 1 or 2. At least we can say that 0 and 3 seem to lose that contest. Well, I guess we'll have to have a look at that. So let me switch over to the problem statement so you can see that as well. Determine dimension and basis for this linear subspace. How do we do that? We have these 3 vectors here. And what we did last time was we just took linear combinations of any 2 of them with the idea, with the goal of producing simpler and simpler vectors until at some point we either produce a 0 row or possibly more than 1 0 row, and the remaining vectors would then be linearly independent. Or we could prove that they are all linearly independent. And you'll remember that basically what we did is Gaussian elimination. Yeah, we just avoided swapping any rows so that we could then go back to the original vectors that we started with. And that correspondence would be lost if we swap rows. So what we do is we take those vectors, we write them as rows of a tableau. And then we try to simplify them using linear combinations of 2 vectors. And simplify means producing as many zeros as we can get. And that's exactly what we do in Gaussian elimination, right? So we start with this here, that's a nice pivot element. We subtract that twice from row 2 and we add that to row 3. And that will produce 3 new lines that have the same span as the old 3 lines, but will hopefully be a simpler description. So the first one is not changed. The second one becomes 0. 3 minus 4 is minus 1, and 1 minus 0 is 1. And this third row becomes 0, 1, and minus 1. Right, and you see we produced a couple of zeros here already. And now in the second step, we take our second row, we take this here as a pivot element, and we go on to simplify. Now 1 0 is below that one. And for that purpose, we just add the second row to the third one. Again, we do a linear combination of those 2. Right, and what we get is 1, 2, 0, 0, minus 1, 1, and 0, 0, 0. And that's the end of our simplification process. And that means what we have here is 2 pivot elements in those rows. So that means those 2 rows are linearly independent. Because if I want to use them to combine the 0 row, I obviously have to have this 0 times because of this pivot element. And then, of course, I need this one 0 times as well, or it won't work out. Right? So there's no other way to produce a 0 row than use each of those 0 times. They are linearly independent. And remember, the span doesn't change by exchanging a vector by a linear combination of any 2. Unless I produce a 0 vector, of course, by multiplying something by 0, which I didn't do. So the span of those 2 is the same as the original span. But if I now take those rows here, write them as columns. So that is the same thing as the span of my original vectors, 1, 2, 0, 2, 3, 1, and minus 1, minus 1, minus 1. So here I have a system that generates my vector space and is linearly independent, so that's a basis. All right, so this here, this is a basis. And that means, of course, the dimension is 2. All right, so almost half of you were right. And by the way, of course, the basis that you end up with, this one here, that is not by any means unique. You could get a totally different basis. Right? The dimension is, so you should also get 2, but you could end up with a different basis. Question? Hmm. So the question is, sometimes we use that formula for calculating the dimension where we say, let's do n, so in this case 3, minus the rank of our matrix, so the number of pivots. And in this case, that would be 1 and not 2, right? So when is this correct and when is the other one correct? And the answer is it depends. It depends on the space that we're talking about. So in this case, we're talking about the space that is spanned by all of these rows. Well, we haven't discussed that yet, but if you watched all these fixed videos, you know we're talking about the row space here, row space of the matrix, right? In this case, this formula applies for the solution space of the linear system defined by this matrix. Right, so that here, that would be correct for that's the dimension, of the solution space of the system of linear equations defined by that matrix and left and right hand side 0. And that's a different thing. Right? I'm not talking about the space spanned by the rows, I'm talking about the solution space. In this case, they are both subsets of R to the 3, but that need not even be the case. So they could live in 2 completely different environments, so to say. And that's why the dimension is different here. Right? So we have 2 different spaces that we consider. And you need to pay attention to which one is considered. Okay, and just to complete that, again, we'll talk about this later, but if you have watched the videos already, that is the dimension of the kernel of A. Yes? Sorry, what was the question? What is the notation? Let me maybe just do an example of that type of question. Is that okay? So the question was, on the last sheet, there were questions that asked you to extend a given set of vectors to get a basis of some higher dimension space, R3 usually. And how do we do this? Well, do I have a nice example for that? Let me have a look. No. Well, I'll just take this one then. So let's say, I mean, we found this nice basis here. So let's just come up with a new problem on top of that. So the task is now extend this set to be a basis of R to the third. And obviously this is a subset of R to the third. 2 vectors in 3-dimensional space. They are linearly independent, we know that already. They span a plane, so they don't span the whole space. They can't because it's just 2. We need 3 for the R3. So can we find a third vector such that these 2 plus the third one will be a basis for R3? And how do we do that? Yeah. Mm-hmm. Orthogonal, yeah. Perpendicular or orthogonal. Correct. Yeah, that's one possible solution. Not my favorite one, but you can do it this way. So the suggestion was those 2 define a plane, and we need to find some point that is not on the plane, and just add this. And one possible way to do this is when we have those 2 vectors. I need another vector. Just a second. Here's my other vector. So I have these two vectors, and I don't have a third one. It doesn't matter. I have these two vectors, and I need to find one that is not on the plane, like this one here. And what I can do is I can compute their cross product. You might be familiar with that. Don't worry if you're not. I can compute the cross product, and will always give me a vector that is orthogonal to those two, so that sticks out of the planes in some direction. I can just use that. And you're right, that will work. The reason why I don't like this solution at this point is we haven't discussed the cross product, and we're probably not going to. And the second one is this only works in R3 because there is no cross product in other spaces. And of course, I'd like to find a method that also works in higher dimensional spaces. And I need to remember to give you an exam problem that doesn't work in R3. So higher dimensions for the exam. So how can we do this not using this cross product here? Is there some alternative? Yes. Exactly. That is a possible way of doing this. Yep. And that has the advantage that it always works in any dimension. Of course, the downside is it's a little more work than the cross product approach. But let's still try this one. Yeah. So the idea is I take these two vectors here. And I consider the span of those two, and also I add all three unit vectors. And if I do that, I can be sure that the span of those is R3. Right? It can't be bigger, because it's always contained in R3. And there is a basis of R3 contained in there. So this is a basis of R3, standard basis, I know that. So it obviously spans R3. And now that I have this, all I have to do is I reduce that. Yeah, so the question is now, can we find a subset of that system here that contains those first two vectors and still spans R3? So in other words, which of these three can I remove? And we know how to do this already. So now I'm back to reducing, right? Let's go through that one more time. Again, we just write that as rows of a matrix, and now we add these three other rows here. And then we do our Gaussian elimination procedure once again. Let's start here. We have zeros almost everywhere. Here's a non-zero, so we need to remove that one. And this is easy, so just copy row 1. We also copy row 2. For the third row, we subtract row number 1. So here we get 0, minus 2, 0. And we copy the other two. Right, so next pivot that we can use is this here. And here where we need to subtract 2 times the second row from the third, and we just need to add it once to the fourth. And we have a 0 here already, so that's good. And what do we get here? Again, copy the first row, copy the second row. For the third row, we have minus 2 plus 2, that is 0. And we have 0 minus 2, that's a minus 2. And here we get 1 minus 1 is 0, and 0 plus 1 is 1. And here we copy the last row. So what do we have? Two steps completed. So let's go for the third one here. That seems Not very nice, but I'll just keep it that way to not interchange rows. So, oops, different color. So I can just add half of that third row to the last 2 rows each. And then I'll have my final result. And obviously those last 2 rows become 0 rows then. Right? And as expected, 3 rows remain. Yeah, we know the dimension is 3, so we need 3 independent rows. Here's the pivot, so those are independent. And that means we can just use the first 2 rows plus that new third one. Or of course we didn't interchange any rows, right? So every row corresponds to the one that we started with. And that means this one here is a result of linear combinations of just the first 3, and of these 3, and of these 3, right? So we could just start with that to obtain this. And that means we can also use this as a basis. Right? So possible bases would be, I take 1, 2, 0, 0, minus 1, 1. And then I can either add this last row here, or if I want to have something even simpler, instead of that last row, I could take the original row that corresponds to it. Oh, sorry, not this one. That was 1, oops, 1, 0, 0. Right? So I just take this because that's what I started with in this third row here. Okay, so I know these 3 are linearly independent, and thus they span R3. So that would be a possible answer. And that, of course, works for every dimension. It becomes more and more work as the dimension grows because I need more and more vectors, and the basis is larger and larger. But I'm starting off with a fairly simple set of vectors here, yeah, just the unit vectors, so that should be sufficiently easy to do the computations. And as I said, in R3, both approaches are okay. Good. Any more questions? That is a bad time to do an update. That does not seem to be the case. Then let's maybe go on. Yep, just a second. Let me switch this off here. Yep. So question is, when do we use the vectors in column form and when do we use row form? The answer, it depends on what we want and what we like. Basically, you almost anytime you're free to use whatever you like best. And that's why I usually use row form, because I'm used to Gaussian elimination in row form. And my advice is to stick to that. Yeah, you'll probably get it confused if you interchange. So row form always works. You might have to transform to row form if you want something different. We'll talk about that in a minute, hopefully. But you can always use row form or column form. Okay, so let's move on. Next topic, matrices. So I was hoping to get through the basic matrix stuff today. That should be easy to do. And then do the multiplication tomorrow. Matrices, very simple definition actually. The idea is just to formalize the notion of tableaus. So, you know, we always use tableaus to solve linear systems. We use tableaus to show that vectors were linearly independent. We use them to compute a basis. So those tableaus seem to turn up on every corner. And that's why mathematicians invented a name and a concept for that. And they don't call it tableaus, they call it matrix. So basically, a matrix is just this rectangular scheme here. It has a fixed number of rows, it has a fixed number of columns. Usually, if I don't want to use actual numbers, I'll say the number of rows is m, and I'll say the number of columns is n, as we did up to this point. And matrices are usually denoted in this way. So if I want to write down all the entries, I do this in the same way that we did for the tableaus. I'll usually use a double index to denote one entry of that matrix. The first index is always the row. The second index is always the column. Right? So the element A3, 17, is in row 3, column 17, for example. Yeah? If I'm not interested in the entries themselves, but just in the general matrix, or if I have defined a name for that, I usually use capital letters for matrices. Mostly they will be called A, B, C, D, and so on. And if I have a short way of defining the entries, I can write it in this way. So I can write it in Aij, I rows, J columns, and I may even put a formula for generating those in here if I want to. Yeah, something like I plus J, for example. Row number plus column number gives the entry, but that will rarely be the case. So this is called a matrix. Usually you'll also include the number of rows and columns. You say this is an M by N matrix, rows by columns matrix. And those things here are called the entries, or the components, or the coefficients, or the elements, whatever you like. The set of all matrices of a certain size is denoted in this way here. So that means all the entries are real numbers. We have m rows and n columns. So this is r to the m times n, or m by n. And for any given matrix, we'll say these here are the rows of the matrix, and these here are the columns, and each row and each column is a vector. So we'll speak of the ith row vector and the jth column vector if you want to access some specific row or column of the matrix. And then, of course, any two matrices are equal if and only if all of their entries are the same. And of course, if their dimensions agree. Few special cases. We will frequently use quadratic matrices, and that just means the number of rows and columns is the same. Yeah, so they form a square. Means they are in the set n to the n by n, so same number of rows and columns. That's called a quadratic matrix. You remember we defined a transpose for vectors already, right? That means transpose of a column vector is just the row vector, transpose of a row vector is the column vector, so you just interchange rows and columns. And you can do the same for a matrix. If you want the transpose of a matrix, you just take all the rows, write them as columns, or vice versa. And that's the transpose of a matrix. So, quick example. Let's say I have 1, 2, 3, 4, 5, 6. That's a 2 by 3 matrix. And I want the transpose of that. Then I take the rows and write them as columns. So I take this 1, 2, 3 row. First row, I write that as the first column of my new matrix. Second row becomes the second column of my new matrix. So 4, 5, 6. And that's a transpose. And of course, the dimension or size changes, right? So this here is a 2 by 3 matrix, while the transposed is a 3 by 2 matrix. So you kind of flip rows and columns. For quadratic matrices, You can, of course, transpose them. The dimensions will be the same. The entries won't be the same usually, but the dimensions will be the same. And then one more thing. A quadratic matrix is called symmetric if transposition doesn't change it. Quick example. So let's say this is a symmetric matrix. The elements on the diagonal of that matrix, if I transpose it, will be on the same position again. So I can choose whatever I want here. Right? Now, for the other elements, let's say I use a -1 here. Then if I transpose this, the first row becomes the first column. So that -1, if I transpose it, moves into this position. That means if the matrix is symmetric, there must be a -1 here as well. Right? Let's say I have a 4 here. Same thing, if I transpose the matrix, that 4 will move down here. So if I want the matrix symmetric, I need a 4 here as well. And then there's one position left. Let's say this is a -5, and I also need a -5 here. So basically, you could say those matrices, geometrically speaking, they are symmetric with respect to their diagonal, right? You could mirror them along the diagonal. Okay, so you only need the entries above the diagonal and you know the ones below, or vice versa. That's a symmetric matrix. And then there's the notion of skew symmetric matrices. It's almost the same thing. But now the transpose is the negative of the original matrix. And if I again start like this, for an example for a skew symmetric matrix, you can hopefully see this won't work out. Because we already said the diagonals always land on itself, right? So the 1 gets mirrored to the 1 by transposition. And of course, 1 can't be equal to -1. So for a skew symmetric matrix, I always need to make sure that the diagonal is zeros. Can't work any other way. And now the rest is similar to what we just did. If I have a -1 here, I need a +1 in that position. 4 here means a -4 in that position. And a -5 here means a +5 here. Right? So this is now a skew symmetric matrix. This one was symmetric. This one is skew symmetric. The German term, by the way, that might not be obvious, for skew symmetric is schiefsymmetrisch. Just in case you ever stumble upon that. All right, so that's basic matrices. And some more special matrices right here that we often need. We've already talked about the diagonal of a matrix. And of course, I can come up with a quadratic matrix that has only non-zero entries on the diagonal, like this one here, right? Or a simple example in numbers, this 1, 2, 3 thing. And then I just fill all the rest with zeros. That is a diagonal matrix. Right? So the only non-zeros are along the diagonal. And of course, that is always symmetric. So that's called a diagonal matrix. And then there are a special diagonal matrix is called the identity matrix. Oops, I wanted that one here. And the identity matrix is the one that has ones on its diagonal. Right? So again, in dimension 3 by 3, it looks like this. Diagonal matrix with just +1s on the diagonal. That is called the identity matrix. And it's usually written as I and then the size as a subscript. So this is I3. identity matrix of dimension 3. Okay, you sometimes also see the notation E instead of I. That comes from the German term Einheitsmatrix. Yeah, so that's also something that you will see frequently. I'll usually try to use I. All right. And now we just need to formalize the terms that we've already discussed and defined in the context of systems of linear equations. We can now say, well, this tableau here that we've talked about before, that basically that is a matrix, right? So this here is the matrix of the left-hand sides. That is the coefficient matrix. And if I add another column as the right-hand side, this is called the extended coefficient matrix. And now I can define the rank of a matrix by simply saying, well, that's the same as the rank of this system of linear equations, right? So I just assume I want it to solve a system of linear equations, and I compute row echelon form for that matrix. I count the number of pivot elements. That's the rank of my matrix. Same thing as before. It's just called matrix now, not tableau anymore. All right, and finally, let's talk about some easy matrix operations. I can, of course, define an addition. I can add two matrices as long as they have the same size by simply adding their entries together, like this. So addition of two matrices, A plus B, that simply means I add all the entries in the same positions. And I can only do this if they have the same sizes. And also, I can multiply a matrix by a scalar like this. So lambda is a real number, a scalar. And I do this by simply multiplying every single entry by that same scalar. So same thing as with vectors. And in fact, vectors are special cases of matrices, right? A column vector is a vector with just one column, so an m by 1 matrix. A row vector is a matrix with just one row, so 1 by n matrix, right? And you can all do the operations that you do with matrices. You can do those with vectors as well. And, well, addition and scalar multiplication work in the same way for matrices, as long as the sizes agree. Well, and it's also easy to see that the space of all matrices of a certain size that you get defines a vector space, because these operations that we just defined are the operations that we need for vectors. We need to add vectors, we need to have a scalar multiplication, and it turns out, same argument as with the vectors in Rn that we used already, turns out that all these properties of vector spaces hold. Right? And of course, the zero vector of that space is just the all zeros matrix. And a basis for that vector space is given by the matrices that have exactly one entry and zeros everywhere else. Right? So the dimension is m times n. Basically, it's almost the same thing as a very long vector that you just get by sticking all the rows together, for example. Okay, so nothing magic about that. And any questions about matrices before we move on to the spaces? Probably not. Good. Okay, and now, again, we've worked with those already, so just want to give those things a name because I'll need them frequently. There's a couple of vector spaces that are associated to a matrix. The most simple ones are the column space and the row space. And those are simply the vector spaces that we get by taking the span of all the column vectors, or the span of, column vectors, or the span of all the row vectors. Yeah, so you remember we've worked with those in the examples that we did today. Right here, for example, so this here, we said this space here, I can write this as the column space of a matrix if I just write all these vectors, as the row space, of that matrix. If I just write all these vectors as rows of a matrix, right? So if this is my matrix A, then this is the row space of A. Okay? So pretty simple thing. Again, that's just giving a name to things that we're using already. And again, that last thing is also giving a fancy name to a thing that we're using already. We can also associate a so-called kernel with that matrix. Sometimes it's called null space, kernel null space. And that is simply the solution of a system of linear equations. So if we take this matrix, any matrix, as the coefficient matrix of a homogeneous linear system, then the solution space of that system is called the kernel of the matrix. Yeah? Again, just sticking a fancy name to that thing. And that's basically it. And the notation for that is ker of A, for the kernel of the matrix. So that is the solution space of the system associated to this matrix. Okay, here's a simple example. Take this matrix here, for example. The column space is the space spanned by the columns. So these three here, that span the column space. That's a subspace of R2. And that means the columns are, of course, not a basis for that space, right? 3 columns, R2 is just 2-dimensional, so the basis can contain at most 2, maybe just 1. So that's not a basis in this case, but as long as we don't want a basis, it doesn't matter. The row space is the vector space spanned by the rows, and usually, just by convention, we still write those as columns if we talk about the space, right? So that means we write them in this way and say, well, the span of those two is the row space, and you can see this is a subspace of R3. And again, if you look at the dimension, we just have 2 vectors, so it can at most be 2. And in this case, you can hopefully see that it is 2, because those are linearly independent. Yeah, one thing that you can prove is that the dimension of the column space and the row space always is the same. The reason for that basically is that you have the same number of pivot elements, no matter which space you look at. And then, last thing, for the kernel. Kernel means we solve the homogeneous system of linear equations. So we do a Gaussian elimination step here. 1 step is sufficient. 2 pivot elements and 1 free variable. So this x3 here, that's a free variable. And then we solve for the other 2. Takes a little work, and what we get is this solution set here. Or in other words, the span of this vector. Right? So the dimension of the kernel in this case is 1. The dimension of the row space and of the column space was 2 for this example. And of course, that is no coincidence. So to conclude this discussion here, there's this theorem that relates those 2 dimensions. Yeah, so I was formerly claiming those spaces are totally unrelated. They're not quite unrelated. The dimension is linked in a certain way, and that link is pretty easy. We've discussed that already. For a matrix, any matrix, the rank of that matrix is always equal to the dimension of the row space, number of pivot elements, and also to the dimension of the column space. That's the same thing. And the dimension of the kernel is, in a way, what is missing from that to get the number of columns. So the rank and the dimension of the kernel add up to the number of columns of the matrix. So if you know one of them, you know the other. Okay? So the rank directly gives you an information on the dimension of the kernel. And that is hopefully clear again, because the rank is the number of pivots, and the dimension of the kernel is the number of free variables, and of course, all of those together, a column can either be a pivot column or a free variable column, right? So all of those together must be the whole number of columns, the n. And that is called the rank nullity theorem. Very famous theorem in linear algebra. And it might spare you quite some work. If I'm asking you to compute both of those, you just need to compute one. And even if I'm not directly asking for that, you should always keep that in mind to sanity check your solutions. Yeah? So if I'm asking, for example, for the kernel, for a basis of the kernel, then make sure to do a quick computation of the dimension when you compute the rank anyway. So it's easy to get a quick check of whether the dimension of the kernel and the rank add up to the number of columns. And if that's not right, then something is wrong in your computations. So you better double check them. Okay. Any questions up to that point? Why is x3 a free variable here in this example, in the kernel exercise? That was this one up here. Yeah, so you remember or not, we started with this one. We did one elimination step. We ended up with these two pivot elements. And you will remember the columns associated to, no, the columns that don't have a pivot element in them, those are associated to free variables. So in this case, this column doesn't have a pivot, and that's why x3, the variable associated to that, is a free variable. Right? And for the others, you can solve using the pivot row. All right. I guess I'll have to scroll through these to see if I can answer any of those. Yeah, maybe give me some time to do this. Is there any more questions in the audience at this point? Good. If that is not the case, I'll go through the questions that have been asked on Tweetback, and I'll see which ones yeah, there is a question. Good. Simultaneously with what? So the question is, can we find the dimension of a column space without finding the pivot elements? Probably not. I mean, you'd have to have the rank. The rank of the matrix is the dimension of the column space. And to get the rank, you'd somehow have to find how many pivot elements the matrix has. So I couldn't think of an easier way at the moment. There are some exceptional cases where this might be easier, and we talk about those, but in general, no. Yes? What does what look like geometrically? You mean the transposition of a matrix? What does that look like geometrically? Hard to answer at this point. Maybe keep that question until in about 3 weeks. We'll talk about linear transformations then and their relation to matrices, and maybe we can get a better answer then. All right. Any other questions at this point? Sorry? Would the basis of a kernel be the basis of the solution space? Yes, the answer is yes. Yeah. So the kernel is the solution space. It's just a fancy name for solution space of the homogeneous linear system associated to this matrix. Kernel is a lot quicker to say. That's all there is to it. All right, as I said, I'll go through the questions. I'll try to answer them online, or I'll pick them up tomorrow. And I guess this is a good point to end today's lesson. And tomorrow we'll talk about the multiplication of matrices then. So see you then.